Welcome. This video gives an overview of a high school learning project that uses industry-level engineering software to support student success with next-generation science standards. This project was made possible by a partnership between ANSYS and the School of Industrial Design, Engineering, and Arts in Tacoma, Washington. The objectives include engaging students with project-based learning in a real-world application of design thinking. This is accomplished through the use of 3D modeling and physics simulation software created by ANSYS and traditional metal fabrication tools found in many high schools. Throughout this project, students are provided with chances to master many of the next generation science standards in math, physical science, and engineering. The most thoroughly addressed NGSS standards are in engineering, particularly number 4, which deals with computer modeling and simulation. Before ANSYS, I struggled to find software that was meaningful, robust, and flexible. The educational and industry-level products provided by ANSYS make this standard easy to achieve and engaging for students. Additionally, since this project deals with force, mass, weight, and material properties, there are a number of great learning opportunities for NGS standards in the physical science domain, such as these two. Since a bracket should remain at rest during use, forces are balanced, which is a specific application of Newton's second law. After identifying the learning objectives, the next step in backwards design is determining how to guide my students to them. My chosen model is the project-based learning model, as summarized in this golden standard definition created by Buck Institute. Their website provides additional resources for those wishing to know more. To structure the project for students, I use a design thinking model created by Stanford School of Design, or D-School. This simplified and linear model allows students to easily understand what they are doing at any point in the project and how it connects to the larger goal. For my class, each step of the project had these specific activities attached to them. In the following slides, I will walk through each part. The project begins with students empathizing about the needs of our client. I reached out to a neighboring school that has an agricultural program. Each spring, they have a large fundraiser where they sell hanging flower baskets grown by the students. The money goes to support the school and local community. The teacher at the school agreed that if my students fabricated and donated brackets to hang those flowers, they would include one with every sale. I created a one-page summary of the features these brackets should contain, including specific constraints on size and standards of safety. Since some criteria require balanced trade-offs, such as low cost and strong design, this document also helps students determine which variables can be adjusted during design optimization. This activity is followed by a quick round of hand-drawn ideas. The defining process continues with an exploration of the properties of our building material, in this case 3/8-inch rebar. Later in the prototyping stage, where students analyze stress in their design using ANSYS's Discovery Live, the results will only be as accurate as the input parameters. So before testing the strength of a design, students conduct 2 labs to determine the density and elastic modulus of rebar. Students determine density by finding the mass of a test sample and dividing it by the sample's volume, which can be done either through displacement or geometry. Since density is a concept addressed in middle school according to NGS standards, this is a good time to focus on teaching scientific notation, since the mass and volume values will be very small when done in SI units of kilograms and cubic meters. Understanding scientific notation and the various ways it is represented will be important later when students are working in ANSYS. A good approximation of the rebar's elastic or Young's modulus can be found by measuring the bar's deflection under an applied force. The equation in the upper left relates a beam's deflection, applied force, length, elastic modulus, and moment of inertia. Since all of these, except elastic modulus, can be measured directly or calculated, this equation can be used to determine this unknown value. This lab provides students with a real-world application of algebra and yields good results. With the project now well defined, students turn towards the ANSYS software. They first get an introduction to Discovery Live and its underlying space claim environment by creating a 3D model of their hand-drawn sketch. In other videos, I will provide support for how to guide students through this process. Next, students are guided through the process of finding a stress solution for their use case defined by the client. The color-coded feedback is immediately intuitive for students, but a quantitative analysis requires a little more work. By editing the material library, students are able to input the values of density and elastic modulus they found earlier in lab. After these changes are applied, they can see the numeric value of the maximum stress present in their design, in this case 52.42 megapascals. For high school students, some support with units and metric prefixes is usually appropriate. For students to determine if their design is good enough for the client, they are introduced to the factor of safety through an additional activity. They know our client wants a factor of safety between 3 and 7, so their stress analysis and Discovery Live shouldn't give a maximum value that is greater than 1/3 the yield strength of steel. Students apply this new figure of merit to their design, using the full power of Discovery Live to make numerous and rapid design revisions. With each revision, they are trying to reach the optimization goal of reducing material and cost while maintaining a desired level of safety and strength. These examples of student work show that they can be quite creative in their approach. Once students land on a design that meets all the requirements of the client, in this case also including aesthetics, they move to physical fabrication. As a construction material, rebar is relatively inexpensive, so I have every student fabricate their own bracket. Tools that we use include abrasive cutoff wheels, bench grinders, MIG welders, and drill presses. These are tools that are commonly found in a high school metal shop. Upon completion of a physical prototype, students move on to testing and evaluation. Our client requested that each bracket be able to support 186 newtons in order to model a waterlogged flower basket. This is the weight of a 5-gallon bucket full of water. During testing, students measure deflection of their bracket and inspect for any cracks or weak welds. Once inspection is passed, students produce a short summary of their process and attach it to their bracket before it is donated to the other school for their garden sale.